So this is the other half of the stoichiometry lecture. For the first one, we did mass to mass problems. So that was the first lecture. This second one is going to use other units. We're going to look at mass, but we're also going to look at moles. We're going to look at volume measured in liters. Okay, so again, you want to have your periodic table handy as well as a calculator. So beforehand, I showed you this mole roadmap where we have mass measured in grams off the periodic table, taking us to moles. We have this mole ratio, which helps us bridge between one chemical to the next. So here's chemical 1, and over here is chemical 2. Okay, so this is number 1, and it helps us change it into chemical number 2. And in the first set of problems on the other video, we did mass to moles, moles to moles, and then moles to mass again. In this one, we're going to mix it up a little bit. We're going to look at volume, we're going to look at moles only, okay? We're not really going to look at particles, okay? Most of the time, we don't use 6.02 times 10 to the 23rd particles in a stoichiometry equation. And that's because oftentimes we don't go back to the lab and count out individual molecules, okay? We're definitely working in mass, you know, in grams, in liters, and occasionally in moles. So that's where we're going to focus our problem solving efforts. So here's our first problem. How many moles of copper can be produced from 125 grams of Cu2SO4? So the first thing we want to do is we want to examine our equation and see if it's balanced. So I've got 1 zinc here and 1 zinc there. 2 coppers here, oh, and there's 2 coppers. And then here's my sulfate molecule, SO4, and my sulfate molecule. So it looks like this equation is balanced and we're good to go. So if we look at the question here, it says how many moles of copper? So I am looking for moles of copper. And I am given 125 grams of Cu2SO4. So that's copper 1 sulfate. 125 grams of Cu2SO4 in order to work this problem. So just like before, okay, we are going to take a look at what I'm given. Okay, and in fact, why don't we go back to the mole roadmap for a moment? So in this particular problem, I was given 125 grams, and I am looking for my number of moles. So this tells me right here, this is going to be a 1, 2, 3 step problem. Okay, so actually it's a little bit shorter than what we've been working before. And this gives me an idea of where I'm going. So I have 125 grams of Cu2SO4. We always start with what we know. Okay, and then diagonal down is going to be the same units, grams of CuSO4. The only place we can go from grams is moles. That's the only stop, is from grams to moles, right there. So I change it to moles of the same chemical, CuSO4. And then diagonal down, same units, moles of CuSO4. Oops. Now watch, I forgot that too. Cu2SO4. I gotta squeeze that in. I don't want to accidentally copy down a number wrong. So Cu2SO4 to moles of what I'm looking for, which is right there. Moles of Cu, the copper. Okay? So we fill in our numbers just like before. Let's get a little different ink color here. I have moles in grams. When I have moles in grams, moles is always a 1. This grams comes off the periodic table. So if I add up copper, I have 63.55 times 2. That's my copper. I have 32.07 times 1. That's for my sulfur. And for my oxygen, I have 16.00 times 4. So I'm going to do the math on each one of these. So 63.55 times 2. That's 127.10, and then 32.07, And 16 times 4 is 64.00. So I'm going to take those molar masses and add them up right here. And what I get is a total of 223.17. So that's going to be my molar mass that goes right here, 223.17. Now, my last thing is moles on top of moles. And when I have moles on top of moles, I get to look at my balanced equation. So next to moles of copper, I need this number. That would be a 2. And next to the Cu2SO4, I have my invisible 1. And so that's all I need for my setup. Okay, because my units cancel out. Grams of copper sulfate cancels with grams of copper sulfate. Moles of copper sulfate cancels moles of copper sulfate, and I'm left with moles of copper. So I multiply the numbers on the top. I hit divide for the numbers on the bottom. Okay, so 125 times 2 divided by 223.17. And this is what I'm getting on my calculator. Okay, and that's enough numbers for us to figure out sig figs. And I look at my initial problem right here, and I've got 3 sig figs. So I want to bring this down to 3 sig figs, which is this right there. That 0 afterwards means nothing. We just drop the rest. And my final answer is 1.2. And check your units right here. Here's my units. Moles of copper. So that is my final answer. Let's box it up in green because green is good. So it's a little hard to read there. So 1.12 moles of copper. That's what's needed. That's the answer to my problem. Okay. So let's do another one. So I have another mole template here for me to write on. This time I'm going from volume to volume. Okay. Now, it's not always going to tell you at the top of the problem. So the way we get this is from reading the question. So how many liters of oxygen are needed to produce 19.3 liters of carbon dioxide? So there's my information to get us started. So I am looking for liters of oxygen, and I am given 19.3 liters of CO2 to start. And again, always make sure your equation's balanced. 6 carbons, 6 carbons. Here's 12 hydrogens. 6 times 2, 12 hydrogens. Count out my oxygen. Here's 12 oxygens plus 6 more is 18. And that would 9 times 2 would make 18 oxygens. So I'm good. Okay, so I always start with what I'm given. 19.3 liters of CO2. In fact, let's go back to our mole roadmap for a moment. This time on this problem, I'm given liters and I'm asked to go for liters. So this tells me I've got 1, 2, 3, 4 steps I'm going to go through. So again, one of those longer problems. Okay, diagonal down, same units, liters of CO2. The only place to go from liters is to moles. That's the only place it can go. So moles of CO2, diagonal down, same units, moles of CO2. Now, this is my mole ratio step. I change it into moles of what I'm looking for, moles of oxygen, diagonal down, same units, moles of oxygen. And lastly, whatever I'm looking for goes in the top box, which is liters of oxygen. So next I want to compare moles and liters. Moles and liters is real easy. I've got that 22.4. I don't need to add up any molar masses. In 1 mole, I have 22.4 liters. So in 1 mole, I have 22.4 liters. Over here at the end, I have moles and liters again. So in 1 mole, I have 22.4 liters. And then my mole ratio, moles on top of moles, comes from the balanced equation. Here's my 9 moles of oxygen and 6 moles of carbon dioxide. So if I multiply this, okay, you might notice that there are some ways to simplify. And that's okay. Sometimes like when we did the STAR test or used to take those or other benchmarks, you weren't allowed a calculator. So you were always looking for nifty ways you could simplify the equation. So see, I have 22.4 cancels out. I could even simplify the 9 and the 6 if I wanted to. But since I'm going to use my calculator, I don't really need to. 19.3 times 9 divided by 6. And that gives me, on my calculator, 28.95. And if I want to round for sig figs, right here, I've got 3 sig figs in the 19.3. So I want to round this to 3 sig figs. So I'm going to keep those first 3 numbers. That 5 is going to round up the 9, and the 9 is going to round up the 8. So that is going to bring us to 29.0. And my units that are left, that don't cancel, liters cancels, moles cancels, moles cancels, moles cancels, I am left with liters of oxygen. So that's your final answer on that one. The liters and liter over liters are really nice because they cancel, but really no big deal to put that information in there. Okay, so again, I'm going to have another clean mole mass one here. This time, I'm going to show you a mole to mole problem. Okay, so again, they normally don't tell you at the top like I am, but I'm just trying to show you some different examples. How many moles of O2 are produced when 3.34 moles of aluminum oxide decomposes? Okay, so I'm asked about moles and I am given moles. Well, if we go back here to our mole roadmap, this is all I'm doing. So how many steps does that look like it's going to be? That's going to be a really short problem, right? 1, 2 steps. So nice and short and simple. So let me clean up my ink here. Okay. So I am looking for moles of O2 and I'm given 3.34 moles of aluminum oxide to start. So that's what I'm going to start with, 3.34 moles of aluminum oxide. And then diagonal down, same units, moles of aluminum oxide. And when I have moles down here, I'm at my mole ratio step. I can change it into moles of what I'm looking for, which is moles of oxygen. And that's it. Okay, I've got moles of oxygen was what I'm looking for. So now I just need to look at my balanced equation to get that information. Next to O2, I have a 3. Next to aluminum oxide, I have a 2. So 3.34 times 3 divided by 2. And that gives me 5.01 for an answer on the calculator. Well, if I look at my sig figs right here, that's 3 sig figs for the 3.34. And the 3 and the 2 are infinite. So 5.01, it actually came out to the perfect number of sig figs. I want my units, and that would be moles of oxygen. So real simple. Okay, just some real basic conversions at that point. So not all the problems have to be long, and I showed you mass to mass first because I think they're the most complex, because you have to get the molar mass off the periodic table in addition to having lots of steps. If you can master that, then doing these short mole to mole ones are very simple. Okay, one more problem here. Mercury 2 oxide decomposes into mercury and oxygen. When 1.25 grams of mercury 2 oxide decomposes, how many liters of oxygen are produced at STP? Well, notice in this problem, I don't tell you what type it is, okay? We also, remember, we should always check our equation and see if it's balanced. So I have 1 Hg here and 1 Hg there. I have 1 oxygen, and over here I have 2. So I'm not balanced. So since I have 2 oxygens on the product side, I need to make 2 on the reactant side. That gives me 2 Hgs, and then here is 2 Hg. So I'm just going to clean this up, okay, and write it out again, 2 and 2. If I interpret my problem, I'm given 1.25 grams of mercury 2 oxide. Now, you don't have to be an expert at naming. What you do have to do is know your elements. Okay, this is oxygen right here. This one is mercury. So by default, mercury should be mercury 2 oxide should be the one with mercury and oxygen in it. So I'm given 1.25 grams of the mercury 2 oxide. And I'm asked how many liters of oxygen are produced. So question mark liters. Now, if you're one of those people who really needs to know how many steps it's going to be, you need to have a little bit more of a plan, always go back to this. This will help you figure it out. I'm starting at grams. I started at 1.25 grams of my mercury oxide, and I am being asked for the number of liters. So that's going to help you see how big your problem is. 1, 2, 3, 4 steps. Okay, so a little bit of a longer problem again. So we start drawing that out. Okay, 1.25 grams of HgO, that's my mercury 2 oxide. Diagonal down, same units, grams of mercury 2 oxide. Up top, the only place to go from grams is to moles of mercury 2 oxide. Diagonal down, same units, moles of mercury 2 oxide. This is my mole ratio step, so now I can change it to moles of what I'm looking for. So moles of oxygen. Diagonal down, same unit, moles of oxygen. And remember to pay attention to your problem, what you're looking for. Right here it tells me I am looking for liters of oxygen. So fill in your right numbers. So now I've got moles and grams. When I've got moles and grams, moles is a 1 and grams comes off the periodic table. So mercury is 200.59 and oxygen is 16.00. So that gives me a molar mass of 216.59. My mole ratio, moles on top of moles, comes from the periodic table. In front of oxygen, I have an invisible 1. In front of mercury 2 oxide, I have a 2. So that's what I put there. Now I've got moles on top of liters. In 1 mole, if you recall, back here, in 1 mole, I have 22.4 liters. So 22.4. Multiply the numbers on the top. So 1.25 times 22.4, because we can skip the ones. Divide by every number on the bottom, divided by 216.59, divided by 2. And I'm going to write it up here since I'm running out of space. 0.064638. Okay, and again, some more numbers. Checking for sig figs, the 22.4 is 3, the 216.59 is 5. Those numbers are infinite. My starting value is 3 sig figs, which is my least. So that's what I'm going to go with. Now remember, leading zeros don't count, but we keep them as placeholders. So we take the first 3 non-zero numbers. I look to the next number around. It's a 3. That means leave it alone. So my final answer rounded is 0.0646 liters of oxygen, O2. That is your final answer. Okay, so there's a lot of different ways we can configure problems. We could have done moles to liters. We could have done liters to moles, grams to moles, moles to grams. You know, so there's all sorts of different combinations that you'll get practice with on your assignment. I didn't show you all of them, but I figure between that and the mole roadmap, you should be able to figure out the different configurations. So be sure to see me in class if you have any questions.